many techniques. The very well-known technique is Viterbi algorithm. Some of you might be knowing that. So there is such an algorithm used here so that these message bits are encoded and they can be decoded very precisely. So what did we do? That ISRO gave us this format and they said that the beacons are sending the signal, our satellites are beaming the signals down, you guys have to build a receiver and this receiver has to understand what the bits are, and they gave us some performance specifications. And those performance specifications are, if I am shouting help me, help me, help me at a periodic rate, how many such shouts should get attention? Maximum number of how many such shouts, and that happens to be 3. The beacon is repeating at 50 seconds, some beacons repeat at 30 seconds. So within 3 bursts, I should be able to completely decode and ascertain the identity and send my response, right? So this was the specification given to us. There are some other challenges in this. Satellite communication is a subject taught here, I believe, so you know that position of the sun and the temperature changes that occur because of that, they drift the electronics completely. So if I am sending something at a certain frequency f, when I am on the other side of the earth, that is shadow, and sun is on the other side, that f will have some value. When the situation reverses, then sun is on my side, the temperature increases by several hundred degrees. So no electronics can really sustain things precisely at the level they were with such a large temperature change. So the frequency changes. So I have it's like a tuning to your the radio channel that you like, let's say 95 megahertz, big FM, and that 95 is changing all the time. So obviously you will not hear your music continuously, it's going to fade in and out. So you have to take care of this, which means whatever algorithms you build, they have to be adaptive. They are knowing what's the frequency now, they're finding out what's the frequency now, and then they are doing what is called the demodulation. So to do all this, obviously, I mean, we had no experience of building a SATCOM system of this kind of complexity. So we started by building first a simulator. Yeah? Like you have simulator. Most of your training, the most critical challenging aspects of that training you simulate, and that's how you become aware of them and you can build your strategies to counter them. So we built what is called a simulator. The lower box is a simulator. And in the world of electronics, simulator can be just a piece of software. So it just creates waveforms and data as though it is coming from a satellite. Or it can be a piece of hardware which is actually sending me signals as though they are coming from satellite. So we chose to do the latter, the hardware approach. So this itself was like a mini project of about a year for us to build a piece of electronics which mimics the satellites. And this piece of electronics took programmable artificial distresses. So I could program that I'm from France and I'm in so-and-so distress, I'm at this location, and the simulator generated the distress signal periodically with all its artifacts like noise and frequency variations and all that. It did that. I think this is a very important aspect of any work, that if you want to do something algorithmically new, first try to simulate the situation, then you understand it completely. And we did this in this case. And this simulated signal then goes into what is called a geolet processor. And this processor is a digital receiver. Again, we'll not go into a lot of technical details here, but sufficient to say that it takes the signal, digitizes it, and once it's digitized, everything happens under software control. Right from filtering to tuning to mixing to demodulation to getting the bits to understand what's the signal to noise ratio, everything happens under software control. So there's really a piece of C++ code, which, if you ask me, is really the geolet receiver. And this is connected to what is called an in-MCC PC. This is the Master Control Center, the Indian Master Control Center in ISRO. And this system receives the beacon messages as they come. So if you sit there, its terminal is always running down, because this is world over, right? From South Africa to Australia, all the time something is always happening. So you're getting messages one after the other. And then the confirmed messages from this, which are real distress situations, are sent to the search and rescue teams. So there are such teams all along the coast. There are also such teams on land. So they get emails. The whole system is wired so that as soon as the alert comes, based on the location, the emails are sent, and then they launch a rescue effort to save people. So again, these are all, I think, a little bit of technical detail. I will not go into that. So this is how the unit looks. Typical instrument on a rack, right? And it has got connectors where the antenna is connected and the receiver signal goes into this connector. There's a bunch of status signal indicators here which tell you if the receiver is working all right or not. And a lot of it is inside the software. And this is connected to a PC, and the PC has displays for either configuration or showing the result. So what I'm going to show you now are sharing of some of the test operations we did. It was something very interesting for us. COSPAS SARSAT, before it approves your country for being an active space segment participant, they run you through their test. I think it's one of the hardest tests I have ever done. And what they do is they emit some beacons from somewhere. I think it was somewhere in the Mediterranean, and they had managed to link it to our satellite. And then we are supposed to receive every beacon that they send up, and they measure the time within which we did. So they do 50 beacons, one after the other, and then they just see how fast you are getting it on your screen. And that report is one of the inputs that they use for certifying your facility. And in this they do challenges like, again I said in the beginning that a beacon can't be a very complicated piece of hardware because it will become very expensive. So it's not possible to control its frequency and all that very precisely. So two beacons, two fishermen buy, may have frequencies which are overlapping, right? So by stroke of luck, if both go into distress at the same time, then you are having a situation where there are two transmissions at the same frequency. So how do you distinguish them? So one, you either distinguish them by the activation time. Most likely they don't activate at the same time because these two are different events, right? So all these conditions are simulated by COSPAS SARSAT in their testing procedure. And it was really heartening, 2 days of solid effort, but then they said you passed and they gave us the certificate. It was really a very proud moment for ISRO and country. So I think these are the satellites, INSAT 3A and INSAT 3D, from which the feed can be given to our receiver. And this is how the operating screen looks. So on this screen, the messages decoded are shown one below the other. So I can see here something from Nepal, something from Tanzania, Australia, and so on. And then type of this beacon, is it like a maritime or used by an aircraft and things like that. Then the message bits, its frequency, its arrival time, its repetition time, and things like that. Now this is how the actual signal is, and I'm very sure none of you spot anything meaningful in this. And this is the challenge. The signal processing has to run a lot of mathematical algorithms to make something or to extract something useful out of this kind of a noisy signal. And this is what our receiver does. So we did 30 active 406 megahertz beacons in a given time for validation of this system. So these are the screens from that. So I will now shift to some real examples, real applications of search and rescue situations. And an interesting experiment ISRO did is called an SRE experiment. I'll tell you how that worked. So this is the SRE-1 experiment. I think this was done in 2007. You're reading in newspapers that India is going to launch astronauts into space, right? And now training is going on. So that time in 2007, it was in very early stages planning of all these activities, and one of the things that they were battling with was how to recover something from space, right? The astronaut has to come down, right? So the plan was to launch a capsule on board a satellite, release it from there, and guide its control in such a way that it falls in water, in ocean, at a precisely given location. Right? Now, then the party will go there and tow them back to the shore, tow the astronauts back to the shore, and so on. So for that, they have to know the location. So the easiest idea that we could think of was, thanks to this receiver, we already have this capability. Why don't we put a beacon on that capsule? And as soon as the capsule hits water, beacon will activate and we'll know the location. So this was called the first space recovery experiment by ISRO, done in 2007. And I think they released it somewhere over America from one of our satellites, and it fell off Chennai coast after completion of its fall. And during this period, obviously it was guided so that it falls exactly at the precise location. And we were there, we were actually invited to especially participate in this. And as soon as it hit water, we could see the India beacon and its message and its location. And this location was plotted using the lat logs, and we could give the exact location to the towing party. The towing party went there and pulled it off and then brought it back to Chennai coast. So this is not a distress kind of situation, but a use of this transponder for an interesting application. Then ISRO did a SRE-2 experiment about 5 years ago, and this was near Andaman Sea, and they dropped it from the satellite again, this capsule. And this time it worked even better, that the beacon was activated right on the satellite. So our receiver even got the altitude as it was falling. So as it was falling, we could get its lat long near Andaman Islands, and we were also getting the altitude as it splashed down. Here there are some actual distress situations. So there was a cargo ship during, I think, Phylline cyclone, Odisha coast in 2013. And this was, I think, a Chinese crew of 17 mariners and some Indonesians. And they were saved because their distress beacon was picked up by us earliest. And then our Coast Guard was notified, and they went and saved their lives. And this was really, that time, a very interesting achievement for Indian COSPAS segment. There was another cargo ship sunk that time, and this also was supported by our search and rescue segment. Chopper crash in Uttarakhand, then some aircraft crash near Chandigarh. This was, I think, again located by our beacon. I recall another event where an Australian solo boatman, his boat capsized about 90 miles from shore, and he had no food, but he had a working beacon, and he activated it there. Very surprisingly, we picked it up before Australians picked it up, and email went from us to government, the authorities in Australia, and they saved his life, and there was a very nice letter sent by them to ISRO. So this is, in short, I have to tell you about this technology. I skipped a lot of detail, being the technical detail, but we can make this a little bit more interactive. If you want to know more technical things, do ask me. And if there are 5 minutes, I'll talk about autonomous navigation sensor. Is that okay?
I have a question here.
Yeah.
I'm not really so I'm asking you a question that why this Malaysian airline, why they could not be pointed out by
Yeah, I think this is a default question in this presentation wherever I have got, that if this is so good and if we cover Australia to South Africa, why we didn't pick it up? It was in those waters anyway. We were called right at that evening, and our people were also continuously looking at the message logs that were coming, because it sometimes happens that you can't confirm all the bits. If all 144 bits are not correct as per the format, then this receiver is going to treat this as interference. It will think that something terrestrial is generating this noise. Maybe there is some malicious interference. People do that. So we ignore it. So we were not ignoring it that time, and we were looking at everything that was the receiver was sensing to see if there is any correlation. But unfortunately, neither us, nor Russians, nor Americans, nobody picked up anything. So I think the conclusion is that the COSPAS SARSAT beacon was not activated. Now there could be two reasons. One is the automatic activation that is supposed to happen on impact either failed to work, which may mean that there was no impact and it was like a very nice glided landing on the waters. It may mean that. Again, this is all speculation. And the other is, of course, what is discussed in newspapers, that this may be sabotage and it was switched off. So these are the possible reasons. There was no emission. And the locations that they got are not from this beacon. They are from the SATCOM that they routinely do otherwise. So Inmarsat picks up those locations, and with that they know that it was the last it was seen in that area. But the search and rescue beacon was not activated.
The beacon, the signal, gets weakened more in the water?
Oh, obviously, sir. If this beacon will not work from underwater, it's above water. So the chance of detection is only on impact and maybe a few minutes or after impact, while it is still floating. Any other question? How is the frequency detected, for example? Yeah, go ahead.
Good morning, sir. So as you told that you have an Indian master control receiver, and you said there are numerous signals coming all simultaneously. And sir, my question was how you decide which are genuine and real messages, as you told that the real messages have been sent to rescue team and all. So my question was
correct. So the 144 bits that I talked about in the beginning, there are some fields in that that packet which can have only a certain pattern. So if that pattern doesn't exist, then it is an interference. It's not a real beacon signal, right? Plus there are some checks. The kind of check I told you, that number of bits added should give a fixed number, So that kind of a check is added to that. Now somebody can, this is public domain information. So if I want to really create a nuisance, I can do artificial signals of this kind and keep sending them. But then you will be caught if you do that. So, because they'll know where the emission is coming from and so on. But it is possible that the system can be defeated by creating the signal artificially. But this is the way we decide whether it is a genuine signal or not. We look at the patterns in the 144 bits and the patterns which are supposed to be there as per COSPAS SARSAT standard. If they are not there, treat this as noise or interference. Yeah, so anything else? No? So, do you have 5 minutes? Because I saw the navigation thing, I'm kind of tempted to show you the 3D imaging thing. I had not opened that presentation, but I'll do it now. Yeah. So again, won't take too long because technical things always, and I've been a former teacher.